Great. We'll go ahead. All right, folks, let's just get settled down here for the afternoon. We're going to get started. All right. Welcome back. I would like to welcome Dr. Eray Aydil, professor of the university's Department of Chemical Engineering and Materials Science. Professor Aydil's research interests range from plasma science, technology, thin films to nanomaterials and solar cells. He holds 7 patents and has won several research and teaching awards. Dr. Aydil will introduce our next keynote speaker. Thank you.
Thank you. Well, welcome back. So I have the privilege and pleasure of introducing our keynote speaker, George Crabtree. He is the director of the Joint Center for Energy Storage at Argonne National Laboratory. He's a professor of physics, electrical engineering, and mechanical engineering at University of Illinois, Chicago. I hope that doesn't mean too many faculty meetings. He has wide experience in next-generation battery technology and integrating energy science, technology, policy, and societal decision-making. He has led numerous workshops with Department of Energy on science and technology and policy. He has testified before the US Congress. He has, as a scientist, over 400 publications, and those publications have received over 15,000 citations. If you're wondering what those numbers mean, it's more than enough to get you into the National Academy of Sciences, which he is a member of. So please help me welcome George Crabtree.
Well, so what a pleasure to be here. It's, and I was just talking to the conference organizers before this session about how inspiring, thoughtful, and lively this conference is. I'm really happy to experience it as well as to help perhaps contribute to it with this talk. And a lot of the themes that we've heard about this morning are themes that I'm going to reinforce. And I have the feeling, having listened to the presentations up till now, that a lot of this will be familiar, but I'm going to put it at a high level and maybe hit some high notes that haven't been emphasized quite as much as they might be. But certainly it will be very consistent with what you've heard before and will reinforce many of the points of view. So I want to spend just a few minutes talking about, over there, the outline, lithium-ion batteries. That's the dominant battery today for the last 25 years or so. And that's when you talk about batteries, that's the battery you're talking about most of the time. Storage in the grid, because as we've heard, especially in the last presentation, last panel discussion, the grid's going to be different in the future, and it's not quite clear what that difference will be, but I want to talk about some of the things that and I will speak from sort of a technological and common sense point of view, not from a policy point of view, recognizing very clearly that policy is extremely important. So are customers, what do customers want, so is economics. All of those things have to come together in order for the grid to change. Well, and talk a little bit about that and then what some of the challenges are. So let's see if I can make this work. Oh, I thought I could. Let's see, what do I do? Push a button? I'm afraid to push a button.
Right side of the circle.
Oh, that.
Yep.
It worked. Okay.
Left side to go backwards.
Okay, wonderful. So, but if you want to know more, here is a review article. It's about 1.5 years old now, I guess almost 2 years old. There's the URL, you can find it. It has some of the things that I'm going to say written down. It talks about lithium-ion batteries and beyond lithium-ion batteries. And over there on the right is our webpage. It changes often. It's updated every week or so, every 2 weeks. And it's a kind of thing where you can go click, click, click. It's a little bit like reading the New York Times. One click leads to the next. So let me start with something about personal electronics. This was transformational. Everything you see in that picture is powered by a lithium-ion battery. It was really the lithium-ion battery that enabled these personal electronics to really take hold. They have been transformational in many ways, so I'm never without my cell phone, except when I happen to forget it, which is not very often because I know it's important. I can call anyone I want, although I almost never call anyone on my cell phone. I use it for lots of other things, like texting, like sending emails and checking emails. And so smartphones have really changed the way we interact with each other. The other way they've changed the world is they've changed the way we interact with information. So if I want to, I can read about the rise and fall of the Roman Empire on my smartphone, if I wanted to do that, very, very easily. So I have access to both people and information, and that's a transformational change. So that's my example of a transformational change. What else is coming? Well, cars, not the subject of this conference, but energy storage is very important for electric vehicles. We all know they're undergoing tremendous changes right now. I put something aggressive there. I think you need a 20K, 200-mile car to really capture the mass market. So we're not quite there yet with the Tesla Model 3 and the GM Bolt. They're at 35K, which is, if you know this, is just about the median price of a new car, and you might think, well, it'll capture half the market. I think that's not true for things like fast charging and battery lifetime, which may only be 8 years, not 16 years. But that's not the topic here, so that's for another time. Here's what we're talking about: grid electricity storage. And it was referred to in, I think Mary Powell said this in the last presentation. We've lived with the grid, our grandma's grid, with one restriction that we're so used to we don't even notice it. We have to generate electricity over here at exactly the same rate that we use it. You don't store electricity. So what does that mean? It means you have to build the grid for the peak demand. The peak demand is about 40% over the average demand. That means you're building 40% more infrastructure than you need. You're operating at peak times, as we've heard, with usually the oldest, the dirtiest, the least efficient, and the costliest peaker plants. And why? Because you only run them a few hours a day, if even that. So why would you go with the modern stuff? So there are implications there. That's a very high-level implication. Lots of lower-level implications that you all know about, you've heard about, but we'll review in a minute. But I wanted to indicate how much energy in the United States is devoted to each one of these three things, and you may be surprised, as I was, how much energy goes into things that are powered by lithium-ion batteries. And it turns out, let's see if I can get this, yeah, it's about 2% or less of all the energy in the United States. By contrast, for transportation, 28%, that's just the gasoline in the tanks of your cars. And for the grid is the big one, nearly 40% of all the energy flows through the grid. So these are much bigger opportunities. They need much bigger batteries than you need for your personal electronics. The safety levels have to be much higher. The lifetime has to be much longer. It's a very different game, although it may indeed be, at least starting out, with lithium-ion batteries. So here is a little history of lithium-ion batteries. So I plotted two things here versus time. One, the red line is the energy density. The blue line is the cost. So the energy density, the lithium-ion battery came out in 1991. Sony brought it out because they wanted to power a little camcorder that they wanted to make small enough to be personal. And at the time the lithium-ion battery came out, it had twice the energy density of the next best batteries, which were nickel metal hydride and nickel cadmium. And in the 25 years since 1991, the energy density has gone up pretty linearly by a factor of 3. So that factor of 3 and the factor of 2, its advantage over the next best battery in 1991, that's a factor of 6. It's that performance that made personal electronics. And if you want to illustrate that in your mind, think about your cell phone or your laptop. If it were 6 times bigger and 6 times heavier, would you have it? Would it be doing everything that it does for you now? Cost was not so important because the battery is a small part of the cost of a smartphone or a laptop. But the cost has been even more dramatic. So it's come down by more than a factor of 10, the blue line there. since 1991, and the news is it's falling faster than we thought it would right now. So go back 5 years and ask what was the projection for a lithium-ion battery. It was a lot higher than you can actually buy it for now. So the question would be, and I think what's going to happen for the grid certainly and also for the car is the cost will be very important. So that could be the driver for the next two revolutions. Can the cost go low enough to really make it work? It's a question that I don't want to try to answer, but it's a very important question to think about. So what do we need to do for the next two things for cars and the grid? Higher safety, lower cost, higher performance targets than for personal electronics. We'll certainly have to learn how to recycle lithium-ion batteries. We don't do that hardly at all at the moment. We may need a discontinuous improvement in cost and performance, just like the one that happened in 1991, to really make these next two transformations work. Let's talk a little bit about the grid. So here on the left are three ways of generating. The flask to the left is supposed to be a nuclear plant. The thing at the bottom is a coal plant. You want to run those sort of base load all the time at their maximum efficiency. By contrast, the turbine on top is variable. So there are different time profiles for generation now. On the other side, where you actually use the electricity, there are also different time profiles. So in a house, like in the lower left, the kids and the parents, kids may go to school, parents may go to work all day, not too many people home, but they're back home at night, and that's when they need the power. A commercial building, like the thing at the top, has just the opposite use profile, so it's packed with people all day, but there's nobody there at night. And a factory, which is the thing on the right, has a third use profile, so you really would want to run it 24/7 all the time. So I mentioned earlier that we have to balance, that is, we have to produce electricity at the same rate that we use it. We sort of learned how to do that without storage. If you had storage, it would be very different. And the best example of storage right now is this. These are batteries that were installed in January of this year at Aliso Canyon, just north of San Diego, because in 2015 a leak was discovered in a natural gas storage facility, which threatened the peaker plants that might operate in California. So with that gas leak, you cannot simply build another gas peaker plant. That doesn't make sense. And the utilities got together and decided to replace, for the first time, peaker plants with batteries. And there are now 70 megawatts of batteries that were installed and began operating in January. So we'll see, after maybe another 6 months or a year, how's it going with that experiment? And this may open the door to actually one of the holy grails of storage, that is replacing peaker plants and leveling loads. We've heard a lot about this already at this conference, but here are all the ways in which you can use storage on the grid. So there's generation, there's transmission, there's distribution. And I don't want to go through all these. I just want to list them so you see how many there are across the whole spectrum. I find it interesting that even in transmission, you can use storage, put a battery at each end of the transmission line, and let that transmission line operate at its peak, most efficient level all the time. You're getting the most out of that transmission line. And you may not have to upgrade it. You may not have to ever replace it. So you can either defer or avoid an upgrade. On the distribution side is really where the biggest changes are coming. We used to have a boundary between the utility and the customer, and that was called the meter. And everything on the utility side of the meter was regulated and controlled by the utility. Everything on the customer side of the meter was unregulated and pretty much up to what the customer wanted to do. That line is now getting fuzzy, as we've heard. So there's lots of things that a utility could do with storage in the distribution grid. Demand management, managing the two-way current flow that we now have because of rooftop solar, and of course infrastructure deferral and avoidance. But there's much more that you can do on the customer side, and the so-called behind the meter, and some of the things that are listed there. I can do that as an individual customer because maybe I'm smart enough to understand it and to oversee the purchase and installation of a battery in my house, and then I could get the benefits. But there's another way, and we've heard about it this morning already, that's the aggregation. So a third party might come in and say, for a neighborhood of homes, let me buy a battery that's sized for the neighborhood. Let me put in an energy management system that's designed for the neighborhood. And if it's a neighborhood of homes where, as we said earlier, not too many people home during the day, but some are, some retired folks or people with preschool children might be home, we'll direct the energy to those houses from the others. We'll supply the services that you need at a lower cost than the standard utility model does, and the aggregator will make a profit on top of it. And the reason you can do this is because not all services are needed by all customers. So imagine that for a neighborhood of homes. Imagine a different system, again with a battery and an energy management system for a commercial building, and of course the third thing, a factory. So you would want 3 different kinds of services, and you could design the distribution grid, a kind of a microgrid, to give exactly those services at a lower cost than the conventional model. What's the problem? Lots of uses for storage on the grid, far more than there are in transportation. May require diverse batteries, not just the lithium-ion battery. You might want batteries that perform differently for some of these different services. And as we've heard, the high cost of storage is what keeps you from doing this now. I was very impressed by the graphic that was up earlier, the survey that we all filled out. The 2 biggest reasons why we don't do storage now, cost, and that was by far the biggest one, but the second one was lack of understanding. And I think this complex system of the grid and where do you put storage, and you have to stack the benefits, or you want to take 5 benefits out of the 15 or 20 that storage could do, put them together and let the battery do all of those things, then suddenly it starts to make economic sense. But how do you make that case? So we really, one point that I want to emphasize, the last one there, we need to analyze the use cases. And here's an example of that. This is a graph from a Rocky Mountain Institute report. It lists vertically some of the applications on the last slide, and horizontally estimates from, it looks like about 10 or so independent reports that are out there on the web of how much value there is in each one of those use cases for storage. And the point of this graph is there's a huge variation in what people think the value is. The biggest one is about halfway down. It's either $900 per kilowatt year, or it's $50 for distribution deferral. So it really makes a difference. We don't know how to do this well. I think this is one of the biggest things that we have to understand. And I would say, from what I heard this morning, we are beginning to understand that. It also matters where you are. So this is a report from University of Texas at Austin. This happens to be, they looked at every county in the United States, at least the continental United States, and they looked in this map, they asked, what's the lowest cost electricity generation for that county? And you see things like wind in the middle. We heard about that this morning. There would be hydropower in the northeast, of course, sun in the southwest, and coal and various things elsewhere. But the point of this is that it depends where you are. So the solution for you, and if you want to say, let's put a battery on the grid and let it do 5 things, the 5 things you want it to do may be different depending on where you are. So location is really, really important.
Pardon me.
Yeah.
Those calculations include capital?
I'm sorry, include what?
Capital? In other words, not just marginal operating costs.
Yeah, so I'd have to go back, and I think it's levelized cost of electricity, but that's a great question. Not sure I can give you the right answer. But the reference is there. We can look it up. Yeah. So where are we going? What I'm seeing is that there are 3 things emerging right now, and I listed them there as axes. Storage going up, distributed energy resources coming out of the plane there. So things like rooftop solar, things like a battery in the garage, things like an electric vehicle in the driveway. And smart, so how smart can we get? Right now, smart grid sort of means smart meter. That's just scratching the surface. We can do a lot more than just smart meters with controlling the flow of electricity. So the little yellow circle says today, and it's small. That means we're hardly doing any of those. And we don't really necessarily coordinate them with each other the way we should. But going forward, we can do all three at a much higher level, and we can make them work together. So that to the extent that they work together, you get a lot more value than you do out of any one or even any two. So that's the way things are going. Here's an example. So the grid of the future will not look like the grid of the past. And here's an example, as I was saying in words before, here it is in pictures. Neighborhood of homes, solar on every rooftop, let's say, electric car in every driveway, let's say, a battery sized for that neighborhood of homes, a management system represented by that computer icon, and a connection to the grid. So you need all of those things, but by coordinating them in the right way and providing only the services needed for that customer base, you can lower the cost, leave room for profit for an aggregator, and just do things in a very, very different way. I wanted to spend one view graph talking about the Joint Center for Energy Storage. That's the organization that I direct. We're trying to make the next generation battery beyond lithium ion. We have, and never mind all these things, I'm happy, of course, to talk about it, but I won't at the moment. We have 4 battery technologies that we like: lithium sulfur, magnesium, which has 2 charges on it, so replace lithium, has 1 charge, with magnesium, 2 charges. You immediately double the energy density, and there's some other things you have to take into account as well. Organic redox flow batteries, we hear about vanadium flow batteries for the grid all the time. Organics give you a lot more design flexibility. Imagine if there are any technical people in the audience. So a carbon ring, 6 carbons, you can hang any pendant molecule off of each one of those carbons, any one you like. They don't have to all be the same. That gives you a lot of design flexibility to give you high voltage, let's say, stability, and all the other things that you may want. And then we have an air-breathing aqueous sulfur battery. Nothing is cheaper than sulfur when it comes to battery materials, and nothing is cheaper than water. And likewise, there's plenty of oxygen just all around us. So we have a new battery design that is the idea is that it's cheap. We want it to be as cheap as pumped hydro, so that you could do long-term storage, things like month-long or seasonal or annual storage with this battery at the same cost as you could do it with pumped hydro. So those are some of the things we're working on. I want to, if I can make it work here, I want to close, whoops. What have I done? Go back. Help. Can somebody in the back just advance?
Oh, there you go.
Oh, good. No, the other way. Okay, that's probably me. Here we go, yeah. So we've spun out 2 companies. One deals with solid-state electrolytes. The other deals with polymer membranes. Let me not say any more about that. And this is what I want to end with. So the energy storage ecosystem, storage is on the threshold in more than one way. We've talked about the electricity grid. That's a big application. We didn't talk so much about transportation. Obviously, that's another application which is intimately connected with the grid. That's how you're going to charge your car. If you look on the left, there's a third one, security, so things like drones and battery-powered soldiers, so to speak. Very important for all kinds of things in these dangerous times. And something that's a little farther off, the Internet of Things. Everything that's on the Internet is going to need a power source, because it's going to have to report up to the Internet what it's doing or what it sees or what its status is, and it'll get a message back from the Internet to do something. So a self-driving car is a perfect example of a thing on the Internet, and the car is going to have to take action. So there's a whole set of batteries that we need there. That's science and technology. The outer ring here is society. And it's a wonderful engine for economic and job growth. It's great for global competitiveness. It's always nice to be there first, not second or third. Great for manufacturing. The Gigafactory is an example of that. And of course, it opens up new domestic and export markets. So there's a lot to be gained from a societal point of view from developing storage. That's it. If you want to read some more, there's a few references here, but thank you very much.
I want to invite now our panel to the stage. We have a distinguished panel who will give us a few minutes of their thoughts on the subject, and then we'll have a panel discussion. Ellen Anderson is the Executive Director of Energy Transition Lab at the University of Minnesota. And prior to coming to Energy Transition Lab, she served in the Minnesota State, getting reelected 5 times between 1993 and 2011. And her signature legislation includes the Renewable Energy Standard. She is one of our own with a law degree, and she has served in numerous leadership and community volunteer positions and received dozens of awards for her leadership in energy. Ed Burgess is the Senior Manager of Strategen Consulting and has served clients in the renewable energy and energy efficiency industries, including several Fortune 500 companies, major energy project developers, trade associations, utilities, and government agencies and foundations. His analysis helps guide regulation and policies in many states across the country. We have Christopher Clack is the founder and CEO of Vibrant Clean Energy. He's an expert in renewable energy, atmospheric science, energy modeling, and optimization. He recently collaborated with Energy Transition Lab and Strategen Consulting to conduct an analysis of energy storage opportunities that exist in Minnesota, which we're going to hear about a little bit today. He is degrees in mathematics and statistics from University of Manchester, United Kingdom. He then went into research and applied mathematics and plasma physics at Sheffield. Among his expertise is also plasma physics, which we have in common. So they're going to give 5 to 10 minutes of their thoughts, and then we're going to have a discussion. And I'd like to start with Ellen Anderson, please.
Great. Thank you so much, Eray. And I'll be pretty brief. I just want to kind of set the stage for the project that I worked with Ed and Chris on. At the Energy Transition Lab, we do a lot of work that involves education and information and analysis. And we work with a lot of stakeholders. And we're at a big research university. And so we incorporated all of those different elements into this project. We set up a series of high-level energy storage strategy workshops starting in 2016 in partnership with Strategen Consulting and Janice Lynn and her team. And we invited 60-some stakeholders, high-level stakeholders, mostly Minnesotans, from a variety of energy-related sectors to come to the table. And we brought in experts from around the country to talk about the state of the art in storage. And it was really about learning and gaining shared knowledge. And then we did some really great brainstorming. And one of the things that we started with was trying to identify what, not storage for storage's sake, but what system needs could we identify in Minnesota and in the MISO region that we thought would be good fits, where storage could be a good fit and could add some value. And out of that discussion, the stakeholders brainstormed and thought a lot about prioritizing our peak demand issues and the fact that we not only have a lot of growing peak demand in our state, but we have something like 1,800 megawatts of additional gas peaking plants in the planning horizon for our state. And so is there a way that storage could be used as an alternative to that? And that's where we brought in Ed from Strategen to really do a use case analysis of that. And I'll get to that. He'll get to that in just a moment. We also talked a lot about MISO as a system. And so we brought in Chris to work on an analysis of over the longer term, what storage would do in the MISO system. So I'm just kind of setting the stage for both of their comments because they did the in-depth analysis and modeling exercises. The last thing I want to really mention from this process is that the stakeholders also brainstormed about what kinds of policies or action steps could be taken if we wanted to begin to take advantage of some of these storage opportunities in our state. And so I just want to share some of those thoughts with you, some of the recommendations or ideas that came out of our brainstorming. For example, we need to learn by doing. That was a very clear outcome of this, that we need commercially viable projects. We need, whether they're demonstrations or pilots, and I think we've heard that a lot today, that they need to be geographically specific. We can't just learn from what California has done. We've got to try it ourselves in our own system with our own conditions. And we talked about how different ways that the Public Utilities Commission could enable that through a procurement process or through a pilot project, authorization, et cetera, and set it up so that it would specifically meet system needs that were identified. We thought we should target, based on the analysis and the results, solar plus storage seemed to be a very timely opportunity in Minnesota. And you heard me talk earlier today about Connexus and their upcoming solar plus storage project, which is a perfect illustration of that. And we heard about that at our workshops. And if we do this again, we'll have them come and talk about it. But right now, they're in the most sensitive negotiation phase, so we couldn't quite have them come and describe their project. We also concluded that we need really better tools. We need, in our integrated resource planning process, we need better modeling that really represents and understands and accounts for the unique characteristics of energy storage, because our current modeling tools don't do that effectively, and they are really based on sort of a backwards look at, or, looking backwards at how we defined planning between, here's what demand is and here's what resources for generation are, but it's much more complex than that when we put storage in and the things that it can do. We need innovative rate designs, we need those procurement processes, we need to figure out how to accurately value the benefits like resiliency, like flexibility, like quick response, some of those things that have been mentioned today. And we need to have market rules that reflect those things, both at the state level, in our regulatory framework, as well as in MISO. And finally, we need continued education, awareness, and learning. And so those are all things that we're going to continue to move forward on. And I really want to recommend this kind of process in your states. If you're not from Minnesota, it was very valuable. And we came up with a final report, which you can find on our website, that really lays out all the analysis and the process. So I'll stop there, and I think it's time to turn it over to Ed, correct? Great.
Okay, great. Thank you. Thanks, Ellen, for that introduction to the process, and thank you all for being here. This is a really great event. So I just want to talk for a few minutes about what we did in our analysis, which, getting to what the lead into this panel, there's an emphasis on looking at specific use cases, and that's exactly what we tried to do here, is to identify a specific use case and look at that and see if storage was a potential solution for that. So is there a clicker, or I can just, yeah. Thank you. So what we first looked at is in the context of Minnesota and what the utility system there's planning environment looks like. As Ellen mentioned, we're looking at, over the next decade or so, something like close to 2,000 megawatts of new natural gas peakers potentially being put in place. And I just looked up the number for MISO this morning, because I know this is the Midwest Storage Summit, and it's something around 16,000 megawatts of new gas peakers that are in the sort of baseline planning scenarios that MISO uses to plan the transmission grid and so on. So, and those are driven by utility planning processes. And so, the question is there, what are we going to do to meet this foreseen capacity need? We have natural gas peaking combustion turbines, which are sort of that default option that often gets put into a resource plan. And so that's there at the top as one potential option. And we've heard today about gas prices being cheap, and that doesn't matter hugely in this case, because these are plants that are run at very low capacity factors. So the fuel price doesn't matter as much as the capital costs. But the other options that we want to look at were standalone energy storage. and then a solar plus storage configuration, and both of these can provide a peaking capability that's very similar to a combustion turbine unit. So the other thing I want to mention is we're in this environment now where we have declining costs for storage, and so there was some studies done that we heard about earlier by the Department of Commerce, but things have advanced since then, and we want to get a fresh, up-to-date look on where things are at with current cost assumptions. So, just as an example, a project went in or is going in Arizona, Tucson Electric Power, for a solar plus storage project with a long-term PPA contract for 4.5 cents. 3 of that was for the solar, so remaining portion for the energy storage. So, and that's a 100 megawatt facility, 30 megawatts of storage for 4 hours. So it's pretty sizable facility and provides some of those capabilities that you might need from a peaking system perspective. So we did some analysis, and just a couple of the steps. We took a net cost approach, which is what we heard about Kelly Speaks-Bachman saying, and looking at not just the cost of the system to install, but also what are some of the additional benefits and revenue streams that could be offsetting that initial cost. And so we looked at a configuration of a 100 megawatt storage system and also a 100 megawatt solar plus storage system. And we looked at these two alternatives, looked at the potential net cost of each, and then saw what the difference was, similar to the way a lot of utility commissions might look at alternative resources in their planning processes under one of the cost test approaches. So we tried to use known techniques for this kind of analysis and come up with an evaluation of the two types of resources. We also looked at the emissions, another important factor in thinking about how we get our greenhouse gas emissions down. So what's the impact of a facility like this on a MISO grid? So that's another thing we looked at. So this just shows you an illustration. On the left, you can see the net cost calculation for the combustion turbine unit, and on the right, in the green, you have the net cost calculation for the energy storage unit. And so we take the initial capital cost, subtract out any kind of benefits we get from any sales of energy or ancillary services, and in the case of the energy storage plus solar, we also considered environmental benefits. Minnesota has adopted policies in this state to account for the value of solar, and so we thought it was appropriate to consider that in our analysis as well. And so just to show you the results here, and it was very interesting to see that for the standalone storage case this is now almost a year ago, cost assumptions, it wasn't quite there in the very near term, but it did look like it might be a cheaper alternative in the 5-year period or so of which is now sort of our current planning horizon. So assuming that there is some cost decline, and as we've heard all day today that we are seeing these cost declines, we think that this type of installation will be cost effective in that planning horizon. And then for the solar plus storage, that looks like it was the case both in the near term and in that 5-year outlook, in large part because we have the advantage of the federal investment tax credit to help with that cost as well. And then finally, a look at the emissions comparison. And this is a little tricky because there's a lot of uncertainty here, how the grid evolves in the future, and the timing and the location of where some of these facilities get put in matters a lot. But what we found is that there's a lot of coal still on the grid. So for standalone storage, it's potentially not a great outcome in terms of emissions, but as there is more and more wind on the system, and wind is on the margin more and more, then you might have a situation where that can help too to absorb some of that excess wind energy and decrease overall emissions. In the case of the solar plus storage, it's a pretty clear winner there. We're generating a lot of renewable energy from that system as well. And so that's just kind of the highlights of some of the results and the analysis that we did, but I encourage everybody to go and check out the report on the web, and it includes not only the analysis we did and a lot of information about the stakeholder process, but it also includes the analysis that Chris Clack did on the MISO system. So I think now we'll turn it over to him to talk a little bit about that.
While Chris is getting ready, I just want to encourage the audience to if they have questions, put them on cards and pass it to the volunteers, so we can start immediately after Chris.
Okay, so as Ellen and Ed have said, this is the system level modeling that we did. I just wanted to start with a little story that I grew up in England. You may have noticed I've got a bit of an accent. We have a country to the north of England called Scotland. It's quite far north. And then at the very top of Scotland is some islands called Orkney. And in Orkney, they're doing solar plus storage to power the entire infrastructure on Orkney, with some offshore wind as well. And I bring it up because it's very much like Minnesota. There's a lot of wind. It's very, very good. The solar, we say, isn't as good as maybe further south. But they're using that with district heating and Tesla batteries to power the whole community. I think it's something like 350 homes at the moment. They're almost passive houses, but they're experimenting it in Orkney because it's dark. And so they want to see how well solar can do when it's dark most of the time, raining. Spoiler alert, it does work. It's a bit more expensive though. So this is a bit different. So we're looking at the bigger picture here, MISO, and then we sort of zoom into Minnesota as well. And what we really were trying to look at was if we did a system level analysis, will it actually allow storage to come in on an economic basis, and then to look at some sensitivities around carbon emissions and see how that plays out. What we used is the wisdom model. It's a model that we developed at Vibrant Clean Energy. And the purpose of the wisdom model is essentially to take planning models and put them on steroids and look at all the big data that we can think of. So we want to look at the high resolution weather data so that we can think about the fuel for the renewable generators. We want to look at disruptive technologies, so EVs, demand side management, DR, storage, which is the big prime component of this analysis, and then see how that all plays together in the short term and the long term. So we looked at hourly dispatch over an annual period, and then did investment periods out to 2050. And so we're trying to combine and use what's called co-optimization to bring these two different sizes of problem together to see if that actually shows co-benefits. So the main results are, as you can probably read on that, that's very large. The electric storage was always picked by 2045 in the MISO footprint. And so what that tells me is, over the 22 scenarios that we used, storage was effective on an economic basis in MISO, even though MISO is ginormous. And so if you've got a smaller grid, then it'll be even more effective faster. And what we found was, we did a previous study with MISO that looked at reducing greenhouse gas emissions by 80%. We found they could do that, but we actually found with the addition of storage, what ends up happening is it becomes cheaper, you need less transmission expansion, and it makes the system overall more reliable. And when we did this, we actually found that by doing that, you drive more solar onto the grid, which is a good thing, and it drives away the fossil fuel emissions as well. Something that was a bit more nuanced is that the transmission is needed to help the storage, but you need less transmission than if you didn't have the storage. So it's a bit counterintuitive, but essentially, it was, as was pointed out earlier, is that it's used for multiple purposes, and the model takes care of that by thinking about that in terms of when to use the storage for different purposes. What we also found is that if you put carbon emission constraints on and you put the ITC on with the storage, much more storage is put onto the grid. And also what we found is that it can support the Minnesota targets quite easily with the storage, and actually it can drive a lot of investment into the state. And so the final result that we found was that it provides lower costs, lower emissions, which sometimes seems a bit counterintuitive when people say that if you want to reduce emissions, you have to increase costs. What we find is if you use a more strategic plan, you can actually reduce costs and reduce emissions. So this is some graphs. I like graphs. What we do here on the left is the emissions percentage compared to 2015. And we drive them down in this scenario to 20% of what they were in 2015. And then on the right, what we're showing is the levelized cost of electricity across the whole footprint of MISO. And so this is the total cost to the consumer. And as you can see, the cost drops down to below what it is today, whilst also reducing emissions quite dramatically. And this is what we see in terms of the installed capacities. On the left is Minnesota, and on the right is MISO as a whole. I would concentrate on the fossils, which is the coal. That's completely gone in Minnesota by 2030. And also in MISO, it's completely gone as well. And some gas is introduced, but we can see halfway along the storage coming into Minnesota, which is about 40 gigawatts of storage into Minnesota. And that changes the resource mix from half coal to being nearly 3/4 renewables or low emissions. I said we needed some transmission for this to happen. It looks like a lot, but when we did the previous study with MISO, we were looking at almost double that amount of transmission without the storage. We need the storage because you have great resources in zones in MISO that are in the north and the west, and you need to bring that in. And that helps shutter down coal plants outside of Minnesota as well, in North Dakota, South Dakota, to bring that wind power in. And then you can use local resources as well. And so this is coming back to the co-optimization. You need both distant resources and close resources to minimize your resource expense. And this is the final conclusions. We did huge amounts of runs, and I spent a long time talking about this with the stakeholders, and you can go online and you can go into all the details if you wish to. But the main thing is that it reduces costs having storage on the footprint overall. It helps bring more renewables on, particularly solar, and it helps bring other benefits that maybe at the moment we don't see because the renewables aren't high enough to actually cause big issues. But when they do, we'll be really, really happy to have storage there to help mitigate these issues. What we find is even if you forced storage onto the grid, even if it was uneconomic, we forced it on, we find that the co-optimization procedure will actually reduce the cost to only about 0.2% of an increase, whilst also reducing emissions by about 3% as well. So essentially what that's saying is that even today, if you put it in, there's no real risk to installing it because costs won't grow too much. And it's a model, so there's going to be error bars on everything that we talk about. So 0.2% when we're talking about $20, $30 billion is a small fraction when you're looking at the amount of storage that we're able to put onto the grid. And so I'll stop there and allow the panel to talk.
Thank you very much, everyone. I, again, encourage the audience to write their questions on cards and give them to the volunteers. But I want to start out by just bringing up one of the survey questions that I noticed when I came in this morning. The question was, what are the biggest barriers to energy storage in your state? And then the largest was cost, and then the smallest was technology. So I'm an engineer, so to me, those questions are, they're actually related, both the answers. So the question is, what is the barrier, technological barrier, that will reduce the cost down even further? The fast decline that's coming now, obviously those are easy, low-lying fruits to pick. But at some point, we're going to reach some sort of a limit, or we have all the technology, we don't need to develop anymore. Any of the?
So I think you're right.
Yeah. Is it on?
You want to take this?
Yeah, I think you're exactly right that it's the cost. And the numbers I hear, and they're probably not current anymore. A couple of years ago, we used to say it's 5 times more expensive to put in a battery to do the job of a peaker plant as it is to put in a gas turbine. That's probably not quite true. Maybe it's only 3 times more, but it's a lot more. And my sense is that's the major thing, as we saw from this survey as we looked at this morning. And to me, that says that the technology isn't quite there yet. So although the technology was a tiny little bar, and I was impressed by that too, and I'm gathering that your studies were with present technology, right, and present battery costs, which I find very interesting. I guess I wouldn't have expected that. But it looks like, indeed, maybe we are at some kind of a tipping point where you could do it now if we could have managed all the regulatory and policy and other things to happen. I don't know, that's my comment.
Yeah, I think just to add to that too, I think it's important to recognize that the alternative that you're competing against, it varies quite a bit too, right? I mean, so we have, and it can be very specific to locations and other things. So putting in a new gas peaker plant in Southern California or in Manhattan, it's very expensive. So, in those kind of situations, I think you're likely to find storage to be extremely cost effective and will be more quickly than in some other places. So, I think in places like the Midwest where there's a lot of open space for development, it can be more challenging. But even in our analysis, we're seeing that we're getting close, and we may be at that sort of tipping point. Costs are coming down on the battery side for sure. There's other costs, including power electronics and just general EPC, that it's tougher to see where you can gain advantages there. But I think that we are at that stage where we really need to start looking at these things seriously.
Yeah, I think part of what we saw with the modeling is as more solar comes online, where it's coming online like a freight train in some of these regions, it actually drags storage with it. Even though it's a bit more expensive in some of these places, it just helps the whole grid manage that solar intermittency or variability that can happen within the day, and it can smooth it out, and it can also extend the sort of output of solar, if you will, through the main peak that happens before wind can pick up or other things can pick up. And so it helps alleviate some of those sharp ramps that you hear about or get with the solar. And so that's what we saw with the model. It was sort of help the solar and storage were working together to help each other onto the grid and with the transmission as well.
I don't have, excuse me, as long as we're all talking, thanks. I don't have a technology answer to that, but I have one answer that's sort of an economic answer, and that goes back to the peak demand, which you talked about, George, in your presentation, that it's just an example of current system operations that we really don't account for the cost of. And I think David Collada said this earlier too, that like the single most expensive thing that customers pay for is that peak demand cost. And so I think part of this, and this is more of a policy barrier and a regulatory barrier and an accounting barrier really about how we account for costs in our current energy system. They don't really pay attention to some of those system costs that we're all paying for that perhaps we don't have policies that push, or economic reasons that push that peak demand lower. And so that's one example where if we could actually monetize the difference between how we could reduce that and levelize the demand and lower it, and at the same time, suddenly the economics would start to change.
Thank you. So I'm going to take some of the audience questions. Some of these are quick. So what energy storage technology did Dr. Clack use in his analysis?
4-hour lithium-ion batteries.
I'm sorry?
4-hour lithium-ion batteries.
Okay. Is there a particular reason? Was that the lowest cost, or?
Ask Ed. Time.
Yeah, so I mean, the analysis as part of this process, we worked on together, and so we wanted to first test the use case of the peaker alternative, and for that we were really targeting the 4-hour lithium-ion, and we worked with vendors who were part of the process to get some up-to-date cost estimates, and so that's kind of the best information we had to go on from the most recent market data, basically. And then we parlayed that into Chris's work, but we didn't spend a whole lot of time looking at alternatives. And as we looked back, we thought actually maybe we should be looking at some longer duration, maybe flow battery type of technologies that could maybe play an interesting role in Chris's analysis.
Yeah, so the main constraint in the optimization model, it tells you what the model outputs tells you what's constraining the system the most, and the thing that was constraining the model the most when we did the simulations was the duration of the storage. So the 4-hour was the main constraint, not the cost of it at that point when we were going further into future.
I have a question here that I like very much. What can be done in Minnesota to better incorporate the externalities of unconventional gas drilling, damage to water, methane emissions, health impacts, etc., when weighing battery plus solar by comparison? Can we factor in climate change, not just carbon?
So Minnesota does have a law that requires a calculation of the externalities impact, but there's one that is specific, one cost or metric that's set for carbon emissions, and there's another one for, I think it's criteria pollutants. So there are a variety of different emissions that are measured, but it doesn't include everything that you talked about, like water impacts or other sort of impacts of climate change. And it's also a planning tool. It's not a market price. It's not a requirement that affects, transactions when you buy and sell, but it is considered by the Public Utilities Commission in the integrated resource planning, and utilities have to account for that when they put their plans together. And often resource choices are made based on that differential in cost, that externality value. And I'll just say that the Commission recently updated those numbers so they're a lot higher than they were originally when they were first set in the 90s. But like I said, they have some limiting factors.
So we do actually take into account that.
To a certain extent, we do, which is really innovative, but it doesn't go far enough in my view. It doesn't really account for it fully in the market, and it doesn't affect market pricing. It doesn't do everything that you suggested.
So this one gets to the assumptions about the lifetime of the solar and the energy storage systems. When you modeled it, what kind of lifetimes were the assumptions, or and is it sensitive, the economical analysis, is it sensitive to those assumptions?
Yeah, sure. We looked at a 20-year lifetime with some replacement costs built in there too, because I think a lot of the, generally, battery replacement might happen in 10 years or something like that. So yeah, that's what we did.
Yeah, and I think we had a fairly high interest rate. I think it was of the order of 7% in real terms for all the capital expenses as well for net present value.
But just a comment, there's another feature besides lifetime. What happens after the lifetime? So if it's a lithium-ion battery and it can be recycled, there's some value there. That may cut the effective cost of the battery by 20%, 30%, some other number. And I think we actually don't know the answer to that. Maybe you guys have found some way to estimate that, but to my knowledge, that's an open question. And I think we really can't make the cost estimates that we need to make until we get some kind of an answer to that question.
That's a very good point. This question, did the study analyze distributed storage opportunities for commercial and industrial uses?
Ours allowed the storage to be placed anywhere in Minnesota, so both on the residential side and commercial side, and then the utility side. But primarily it was mostly built, if not all, I think if my memory serves, on the utility transmission side of the model. It didn't build much in the commercial side.
Yeah, we really focused on the larger utility scale systems because of some economies of scale that you can get from that. But there is a thriving behind the meter commercial storage industry now, so that's certainly worth looking at.
So this one says, many folks think about plugging their EV into their house. What major obstacles are there for plugging our house into our EVs?
So I saw a beautiful video demo done by Nissan. They took a single Nissan Leaf, one of the new ones, took it to a rock concert, which was held outside, and powered the whole thing from the Nissan Leaf. And this is, for hours. I found this to be amazing, but you can apparently do it. So I think there's a huge opportunity there. The question is provocative, I think, rather than, there is no answer to that. But yeah, we ought to be thinking about that.
Keep imagining. On that note, I think we're going to end. I'm going to thank the panel here for their thoughts, and thank the audience for their questions.